All right, it's time for the Chapter 8 study guide on confidence intervals. And I think out of all of the things we talk about in AP statistics, confidence intervals is my favorite topic. So, this is my favorite chapter in the book. And there's a lot of really good stuff that we've got to cover here. So, let's go ahead and jump in. Looking at our first problem here, we're looking at building a confidence interval on the proportion who support healthcare, and we are looking at a couple different confidence levels. So the original interval that they give to us is 95% for the confidence level, and this congressman wants to switch it up and make it 99% confident instead, keeping everything else the same. So it's still the same sample, didn't get new data or anything like that. They just straight up changed the confidence level. So the formula for a confidence interval on P is written right here. You start out with your point estimate, P hats. And then to get your interval, you add or subtract this guy right here, which is called the margin of error. That whole thing together is margin of error. And it's built into two pieces. There's the critical value, which is Z star. That is based on your confidence level. So your confidence level is going to affect the Z star. And then you've got your standard error for the graph of P hats for your test statistic on the problem. If you go from 95 to 99% confidence, let me try to explain just conceptually. This is the easiest way to do this one. If I'm 95% confident that I'm going to capture the right answer, and then I want to be 99% confident. If I want to be more confident I'm going to capture the answer, I'm going to reach my arms out wider so I can cover more ground. So when you raise the confidence level, you actually increase the size of your interval. You increase your margin of error, which is good in the sense that you are more likely to catch the answer, but it's bad in the sense that a wide interval is less helpful. If I tell you the temperature tomorrow is going to be between 0 degrees and 100 degrees, I'm probably right, but I'm not being very helpful either. The other way mathematically you could think about this problem, if you change to 99% confidence, your critical value is going to get higher. If your critical value, you could try it with a 95% and a 99. The 99% number is bigger. And if that's a bigger number, you're going to get a wider interval. So correct answer for this first problem here is that your new 99% confidence interval will be larger or wider because higher confidence requires a larger margin of error. Our second problem here is still talking about percentages. So we still want the formula you guys can see written above right there. And for this example, what we're doing is we're looking at 200 people, and we find in our sample of 200 that 25% are strongly opposed to a state lottery. They ask us for the standard error of the sample proportion. Sample proportion is P hats. So they want to know the standard error of P hats. Remember, P hat follows an approximately normal distribution, and what you would do is the mean goes to P, and the standard deviation for P hat's graph is that P1 minus P over N formula. You guys have seen this formula plenty of times. This guy that I'm writing right now with P's in it refers to the standard deviation of the test statistic. The standard error goes into the fact that in a confidence interval problem, I won't know what P is. That's what we're trying to estimate. So what we do is we use P hats instead, and that makes it a standard error. So what they're asking for in this problem, sometimes it's difficult just to figure out what they even want. They just want the circled guy for this problem. That circled thing is the standard error of the sample proportion. So all I would do with this, it's really easy once you figure out what they want. My sample proportion was 0.25. So I'd do a 0.25, a 1 minus 0.25, and I would divide by the square root of my sample size, which is 200. And if you type that into the calculator, you should get a standard error of 0.0306, which is choice B. Third problem. Looking at this example, this is one that is talking to us about figuring out our sample size to account for a certain margin of error. So it's actually still going to be helpful to have our little formula handy. The margin of error is the thing after the plus or minus sign in your interval. You start at P hats. The margin of error is what you add and subtract on each side to figure out how wide your interval is going to be. So when we do this problem, they are asking us to compute this guy, right here. That's going to be our margin of error. And we want the margin of error to be no more than 3%. So I'm going to write down my little formula right here. And when I do that, I'm going to do a not or a less than or equal to 0.03. So in one of these problems, we're going to plug in for the stuff that we know. And we should know in this problem everything except for n. So n is the thing we don't know. This might end up being under my face when I actually record this. Let's see if that makes it better so you guys can actually see what I'm doing there. So with my little setup, I need to make sure that I have everything plugged in where it's supposed to go. My critical value right here, that's z star. Remember the way that you get z star is you do a middle area of 95%. So my middle area has to be 95%. And if it's a 95 in the middle, my tail is 5% divided by 2, which is 0.025. So what I would need to do to get my critical value is I would do an inverse normal. If you have the ability to do center area, you could just do center area 0.95. Most of you, though, on your older calculators probably just have area, which means from the left. So you would do this guy, area of 0.025, and then you would drop the negative on your answer. If you do all that, you should get a critical value of 1.96. So make sure you're familiar with how to find that. And then in this problem, if they don't give you a value for p hats, the worst case scenario is using a 0.5. So that's what you should do, is you should use 0.5 because they don't give us any other indication. We don't know n, and then we have less than or equal to 0.03. This is getting really messy, and I apologize. Now you're just doing algebra. You're just basically plugging and chugging and moving everything over to get n by itself. So I would divide by 1.96. Then I would square both sides to cancel the square root. Then I would multiply by n to get it out of the denominator. Then I would divide by that whatever decimal it says on that side. If you do all that math, you're going to get that n is greater than or equal to, it's like 1067.1. Always bump it up to the next biggest whole number. So if 1067 was a choice, that would be wrong. But luckily, they weren't tricking us that badly here. Correct answer is going to be 1068. Bump it up to the next biggest whole number. So let's carry on with our second page of multiple choice. Now we're getting into X bar problems with means, and this first guy here doesn't take a lot of work. It asks what sample out of these, or which samples, would be appropriate to do a t interval. For a t interval, if our sample size is at least 30, we're golden. We can use it, it's great, just like we would do with the central limit theorem last chapter. Unfortunately, none of our sample sizes are going to be 30, so that's out. Now, ordinarily, that would be a bad thing. Like if this was last chapter, we'd be like, oh gosh, we can't do normal CDF, and it'd be done. But the t distribution is called robust, meaning that it's actually does an okay job of getting you a pretty accurate answer, even if your conditions aren't exactly met. What we need to make sure of is two things. We cannot have outliers in our sample data, and we also can't have super strong skew. Both of those things are going to be bad where the t distribution isn't going to be great. But if you have relatively symmetric data with no outliers or even a tiny bit of skew, the t distribution should do a good job with this. Because what we're basically doing by graphing our sample data is we're saying, could the population actually be normal? Could it maybe be normal? And if it's not too skewed, you can say, yeah, it probably is. The t distribution works out. So long story short, this guy has an outlier right there at 2. That's not going to work for our t distribution. This middle guy is strongly skewed, so that would be out. But this third graph, even with the sample size of 11, relatively symmetric, no outliers, nothing to say the population couldn't be normal. So that is going to mean that sample Z is the only option out of those 3 where we could do a t distribution. Answer is choice C. Our next problem right here is looking at a confidence interval. And incidentally, they wrote their interval as an inequality here, which is totally fine. What they got for their answer was from 3525 to 4425. Never write your interval with a little subtraction sign like this, like a dash. That's bad notation on the AP test because it's ambiguous whether you mean subtraction. So if you're ever reporting an interval, don't do what I just did right here. Instead, what you need to do is you need to either write the word 2, like from 3525 to 4425, or just use our interval notation, which is this guy with the comma. So this is what their interval is. They did a 95% confidence interval, and they want to know what the interpretation is of 95% confidence. This is asking for the script for a confidence level. Confidence level says if you make lots and lots of intervals, what percent of them approximately would capture the real answer, whatever it is? We don't actually know the real answer in this problem. The government's claiming it's 4,500, but we're trying to capture whatever the real answer is. And when you do this, do not mention the word probability in your answer. Probability with confidence intervals is like a touchy area. You don't want to talk about it that way because the answer, whatever it is already established. So avoid talking about probability. And if you look, choice A mentions probability, choice B, choice E. Avoid talking about probability in confidence interval problems. Correct answer, saying what I basically just said, is that 95% approximately of our intervals will contain the true value, whatever that may be. That is choice D. All right, our final multiple choice question here gives us our little interval. And remember, this is going to be a mean problem here. We're building a confidence interval on mu. So we start out with our sample mean. We would have a t star for our test statistic, and our standard error formula, instead of sigma over root n, we're going to have our sample standard deviation s over root n. And they ask us to figure out the confidence level. Confidence level is going to come exactly from this guy right here. The critical value is what we need to figure out, basically. Now, they give us other information in the problem. They, first of all, say that the margin of error, the whole thing after the plus or minus, is a 47.8. So this guy right here has to equal 47.8. I still don't know t star. That's going to be what I find to get my answer. So t star is still unknown to me. The sample standard deviation is 95. And I have to remember to divide that by the square root of my sample size, which is 30. So I have this, and I have that equals the 47.8, which is my margin of error. The 95 divided by root 30 thing is like equal to 17 point something of, I don't know where it is right now. It's 17 point something. But if you divide by that, you should end up getting a t star value of, it looks like you get 2.756 if you just solve this algebraically. 2.756. Now you have a couple options because I know my critical value, but they wanted to know the confidence level. Easiest way to do this one, the critical value is I got 2.756 right here. If I know the negative version of that number as well, so I'm going to do negative 2.756. If I can find the area in between those two things, this area right here, that is going to be my confidence level. That's the easiest way to do it. So I'm just going to do, it would be a TCDF. I'm looking for the area. If I knew the area, I would do inverse T. I would do a TCDF on this problem from negative 2.7 to positive 2.756. And then when I did that, my degrees of freedom would be 29 because my sample size is 30. If you do that, you're going to get an area of 99%, which is choice C. So the confidence level is 99%. Oh my gosh, what's going on? Something happened. Oh, this is devastating. Oh, wait. Oh my goodness. Google, you're killing me right now. Gotta type in my password. I do not want to redo this video. I'm like 15 minutes in. Sorry, guys. So you're just gonna have to deal with that unless I feel industrious about cropping the answer or whatnot. Okay. Do I have a pen tool? It made my pen tool disappear. This is really sad. I'm gonna have to splice this video together and it's gonna be a whole thing. All right, so our free response question for Chapter 8. This is actually a question that I really enjoy. It was off of like the 2017 or 2018 test just a couple of years ago. And what's happening here is we have an environmental science teacher, and they are looking at what percent of students at their school actually recycle. So the teacher's calling the students into the office and asking them one-on-one, hey, do you recycle plastic bottles regularly? So we'll talk about the methodology and the design of this experiment when we get to part B. But part A is giving us some information about the confidence interval and asking us what the sample size was. So the first thing you need to recognize on this problem is that the answer is a percentage. It's a P problem because we're looking at the percent of students who recycle. So with this, we know our little setup for our interval would start out with a P hat plus or minus, we'd have our Z star critical value. And we would have after the critical value, our standard error, which is our P hat 1 minus P hat over N setup. So what's going to have to happen in this problem, because they don't just say what the sample size is, we're going to have to work backwards with our nice little formula right here and figure out what N is going to be. Now, for margin of error style problems, you use a 0.5 for p hat because we don't know any better. But you can actually find the exact p hat value in this problem. And if you use a 0.5, you'll get it wrong. The way you do that is you look at the interval that they give you right here. If that is your interval, remember the center of your interval before you spread out your arms for the margin of error is exactly your sample proportion. So I'm going to figure out what p hat over here is by figuring out the midpoint of my interval. I'm just going to average those two numbers. If you average them, you're going to get a 0.7. So the p hat for this problem is a 0.7. And after you do that and find the average, you'd show this work in more detail on your own test. The margin of error for this problem is going to be the thing after the plus or minus sign. It's from 0.7 to each edge. So 0.7 to 0.816 and 0.7 to 0.584, same answer. The margin of error is going to be 0.116. I just subtracted the 0.816 from 0.7. So all of this guy right here has to equal 0.116. That's my basic setup. So Z star, you can do the critical value like I've showed you before. You're going to get 1.96. So I'm going to have 1.96. And after that, I'm going to have my square roots with a 0.7, 1 minus 0.7, which is 0.3, over, I don't know N, but I know that quantity has to equal 0.116. Once you have this set up, I did a very similar problem earlier in the video with the margin of error. You just get N by itself, do algebra. You're going to get 59.9 or something like that. So the sample size is going to be 60. So 60 is our sample size on that first one. So let's talk about this problem real fast and talk about why the sampling method that I described earlier for this teacher is biased. Say I'm your environmental science teacher. I pull you over one-on-one, your environmental science teacher, and I say, hey, do you recycle regularly? If you don't recycle, you're going to feel kind of bad about that most likely, and you're going to be a little bit guilty if you feel a little bit guilty if you don't recycle. You're not going to tell me that. So there's a good chance you may lie and be like, oh yeah, I recycle, even if you don't. So that is the major issue with this setup right here. Asking somebody in person when they're talking to their environmental science teacher is likely to lead to some dishonest answers because people are embarrassed. So this is what I wrote for my answer right here. And you can read through that and write that down yourself. But remember, there are two things you must do when you talk about bias. One is identify the source of the bias. I'm your environmental science teacher. You might be embarrassed to tell me if you don't recycle. The second thing you have to do is talk about whether that'll lead to an over or an underestimate of the real answer. So if people are lying to me, my estimate for the percentage is probably overestimating. It's probably higher than the actual percentage. So make sure you address those two features in your answer like I did right there. And then our last problem right here with this is actually really cool. I like this. It's a neat way, and I think the purpose of this problem was kind of just to teach you guys about something you can do to get better data without making things anonymous. So what you're supposed to do is on your own, you flip a coin. And I'm your teacher. I don't get to see you flip your coin. You just flip it. And then if the coin lands on heads, you tell me, no, I don't recycle, no matter what. So you could actually recycle. And if you go in there and your coin lands on heads, you are obligated to tell me no. Okay. So what that does for us, half of my data is going to be useless basically, because half people said no just because. Okay. But let's say I'm a kid who doesn't recycle. If I flip a coin secretly and it lands on tails, so I'm supposed to be honest, I'm more comfortable now, possibly saying the truth, saying, no, I don't recycle, because my teacher isn't necessarily going to judge me because they might think, oh, their coin just landed on heads. So you get half of your data that's kind of whatever, not very good, not helpful. But for the remaining half, you're presumably going to get more honest answers. At least that's the theory, because there's no shame in lying. You can tell the truth right now, and there's no shame in saying no. So what is the expected number of people in a sample of 300 who will say no just because the coin flips lands on heads? This feels like too easy, but it's really setting you up for the second question. Half the people, approximately, are going to say no just because of the coin. That's 150. Make sure you show your work, half times 300. The last question here is the one that they're more interested in. Out of 300 people, 213 said no. So 150 approximately of those people said no because of the coin. So what I would do is I would subtract out 150. And if you do that, that leaves 63 no's out of 150 remaining. So I would subtract 150 from each of those numbers, and that's like throwing away the useless data from the coin flip. That leaves me with this much good data. Now that is people who said no. So my estimate for people who said yes would be the complement of that. I would do a 1 minus on it. That leaves me with 87 out of 150, which makes my estimate for the true proportion of people who recycle without the shame and dishonesty in there is about 58%. So this problem is a neat little walkthrough on something you can do to avoid dishonest results in your own data collection. The second problem here is going to get into a 4-step, so it's good to practice those. We were once quite good at them, but it's been a little while. So go ahead and you can work through that one on your own. I don't have much else to say about that second question, but yeah, thanks for listening.